Okay, so our continuing our session on buffers and timing, which again is one of the really interesting things about ST2110. We have Nemanja Kamenica, who is going to be talking about a buffering walkthrough. So how do the buffers change as you go through a system from end to end, and you'll get some new insight on how all these things should be set up properly to work with switches and routers and all that other good stuff. So take it away.
Thank you. Hi, everybody. Thank you, Wes. Yeah, I'm going to talk about the buffers today. I don't know if that's an interesting subject here, but I kind of have a lot of experience, not just for the broadcast, but also general networking perspective, and I'm going to talk how it happens in general and how that reflects to the broadcast system. My name is Nemanja Kamenica. I'm technical marketing engineer at Cisco. It says here. I don't have a big one. With this, as I said, first brief introduction, what are the buffers, and I'm going to talk about those. After that, I'm going to introduce you to type of the buffers, specifically to VOQ and egress type of the switches, and then I'm going to tell you how those buffers are used for unicast and multicast traffic. That way you understand what are some of the challenges, common challenges in each of the architecture and how they're similar between those two. As both of the unicast and multicast are part of the broadcast studio, usually your live traffic, it's multicast, and your file-based traffic, it's usually unicast in this case. And then let's talk and let's see what are some of the gotchas, how that buffering affects your broadcast networks. And in the end, I'm going to tell you how to implement QoS on your network in order to overcome most of these challenges which you have. With this, I'm going to start and talk about what the buffer is. Basically, what the buffer is, it's a piece of a memory which sits on the switch. It's a hardware resource on the switch or the router, a networking node. And in this case, when the packet comes on the switch during the lookup and during processing of the packet on the switch, it sits in the buffer for a brief moment. And at the time when it needs to leave the buffer, it's scheduled and leaves the buffer and leaves the switch, goes on the wire, how we say that in the networking world. In what cases buffer it's used? Usually speed mismatch, a speed conversion, and also in case of the traffic bursts, as well as conversation many-to-one, or in this case, let's put it, or subscription case. I have two diagrams which I want to show you here. The first one represents that communication many-to-one, and that could happen for unicast as well as for multicast traffic. What switch does, it buffers that traffic, eventually reaches the end of the buffer and drops that particular packet. This is what we want to avoid. And from this perspective, there should be enough memory to absorb this kind of burst to a reasonable matter. But if you are subscribed all the time, of course, there is no, it's a finite resource, and that way you need to use it smartly. The other case is that we have a speed mismatch, and in this case, we have multiple clients of 1 gig talking to a 1 gig client, but the network in between, it's 10 gig. And at this given point, when this particular switch forwards traffic to this particular switch, it sends it at the 10 gig speed, at the rate of the 10 gig. But then when the host receives that packet, they receive it at 1 gig rate, which is 10 times slower, which means the networking equipment needs to buffer that packet. As long as the resources are there, switch will buffer that packet, eventually will start dropping it, and that's basically where the trouble means. Why I show you these two particular scenarios? Because they are most common, and you should design your network to avoid this, but I will cover that in a later slide. With this, let's talk about something which is called queue and queuing operation, as well as scheduling. Usually buffer is divided into logical portions, which we call queues. And in this case, those queues are dividing dividing different classes of traffic. You can treat your traffic in a different way. Let's say you will treat your live traffic in a certain way versus your file transfer in a different way versus any other traffic in your network, which means they all can be part of the same network, but you need to understand what they are. And then you treat them differently. In this particular case, scheduling is that operation, how you treat them differently. Reason behind it, you will schedule some traffic or you will forward that traffic faster than the others. For example, your multicast traffic as a live traffic, you will most likely forward it first outside of the networking node and outside of the network because it's very, very sensitive. Versus your file transfer, let's say that's for the backup, it doesn't need to hurry because it will be backed eventually somewhere, nor anybody expecting it, and that way it can be forwarded slower in that case and use a different properties of the network. When we talk about scheduling, basically that's dequeuing or draining queues or traffic from the queues. That's operation of the scheduling, and there is different algorithms which allow you to do that operation in a different way. I'm not going to cover those, but I'm going to tell you difference between two types of the queues. We have something which is called strict priority queue. Strict priority queue is the queue which drains no matter what's there on the switch, and it doesn't care about anything else but the traffic which is in that particular queue. That's why it's called strict priority, because I have my priority, it's always the most important, and I'm going to send it first. Where would you use this kind of a queue? Usually for your live traffic, because as I mentioned, it's very, very sensitive, and you would want it to forward it no matter what else is there. And then you have your regular queues or your normal queues, which are lower queues than strict priority queue. What that means, only if strict priority queue is empty, your normal regular queue will get some scheduling resources and forward that traffic. That's why I said when you have a file transfer, you would most likely use one of the normal queues because, as I mentioned, that traffic, it's not that sensitive in terms it will eventually get to destination. Is it immediately or a few microseconds later? Nobody cares. But if your live traffic is delayed by a few microseconds, you're going to care that a lot. With this, let's talk about buffer types. As I mentioned, where the buffer is used, how queues are present in the buffer, in the memory itself, how divide that physical memory into logical pools. And then let's see how buffer looks like from the memory perspective. There are two types of the buffer. The first one is called VOQ, which means virtual output queuing. How the buffer looks like from the networking node perspective. Majority of your buffer, it's in the ingress side. Basically, when the traffic is coming to a networking node, that's where it's going to be buffered. And I will explain in each of these types briefly in the next slide or next slides. The other type of the buffer, it's output queue buffer, where majority of your buffer is on the egress side, or mostly all of your buffer is on the egress side, in most of the cases shared among the egress ports. Why the virtual output? I got to speed through this, but let me slow back a bit. Output queue buffer, as I mentioned, this is shared, but queues are dedicated per each of the port. And this is efficient way to do it. In order to have same kind of principle in the VOQ, what you have done is that you mapped virtual queue. You're simulating in your ingress buffer your egress queues, and that's why it's called virtual output queue. Make sense? Okay. Let's take a look at the virtual output queue, and let's see what are some of the properties of the virtual output queue. As I mentioned, majority of the buffer it's ingress side, and as I wrote over here, majority 90 to 98% of the total buffer on the particular switch or particular ASIC is attached to the ingress port, and only small portion between 2 and 10% it's attached to the egress port. As I mentioned, in the virtual output queue, each of these ingress ports has virtual output queues to all of the egress ports, which means this ingress buffer is divided into multiple other queues and simulating the egress ports. This buffer is suitable for the external buffer architecture. If your switch or your, not switch, but the ASIC which is present on the switch have an external large buffer, big buffer, how we call it, this is usually how the architecture works. Reason behind it is easier to implement and divide that larger buffer into smaller queues that they can satisfy any kind of need. Where do we see use for this? And when we talk about unicast traffic, this is what we have here. Oh, sorry, go back. Most file-based workflow are unicast-based, and they're going to use majority of that ingress buffer which is present there. However, in the VOQ architecture, we have super small portion of the buffer which sits on the back, which I mentioned in this first paragraph, and that multicast buffer or that egress buffer which is present here, it's used for the multicast traffic. As I mentioned, let's say that there is 100 megabyte of buffers present on the particular switch. Let's say, in best case, 90% or 90 megabytes will be here, and 10 megabytes will be in the egress side, which means if you have multiple multicast streams sending towards single destination, we always subscribe that destination, there is only small portion of the buffer which can catch that traffic. Versus if multiple unicast streams are sending to the same destination, you oversubscribe the destination, there is much larger portion of the buffer which can absorb that kind of traffic. The other thing which I would like to mention, it's something which is called head-of-line blocking. What head-of-line blocking does, basically, let's say that we have one sender sending to multiple destination, multiple egress destinations, and in this case, there is 3 of them. And let's say that one of them, it's experienced congestion on one of the egress ports. This is this bottom right corner here. What's going to happen? Basically, because that one port experienced congestion, it will be back pressure to the ingress buffer to preserve that traffic, and eventually when that buffer is full, it is going to drop. But it's not going to drop only for this particular port. It's going to drop for all other ports. All 3 ports will suffer from this perspective. If this is unicast traffic, that VOQ architecture which I explained, it's going to satisfy this requirement because each of these ingress ports will have their own particular queue which maps to the egress port, and we will only saturate or we will pause only that particular queue for that particular port. However, if this is multicast traffic, and for whatever reason we decide to buffer traffic in the ingress buffer, which is usually and in most cases not the thing which will happen, we will experience the same congestion. But from a different perspective, let's say that you have multiple destinations which are receiving the same multicast group. If one of those destinations is congested, basically all of the destinations will suffer for that multicast queue, for that multicast group. With this, let's take a look at the output buffer queue. As I mentioned, the output buffer queue, usually resources and buffer is shared for all the ports and all the queues. And each of the egress port has its own belonging queues. Basically, the buffer it's represented from that perspective and divided to each. Buffer, it's also dynamic in this case because it's shared. Each of the ports should have access to it, but in dynamic fashion. That way, in case of a congestion, I can take more, but if I'm not congested, I can give it to somebody else to use that portion and that resources. And also, every port has its own queue. That way, we avoid head-of-line blocking scenario because each of the queues and each of the ports will get only their own stream. They are not dependent of the others. And this is usually how on-chip buffers are made in this kind of architecture. Basically, buffer which is on-chip dedicated to the ASIC, it's usually in this kind of fashion. One other thing is that if we talk about broadcast streams, 2022 there's 6, 2022, 2110, 2059, all of them are multicast streams, which require low latency and low jitter. As soon as I get the packet, I want to forward it to the destination with least delay which I can provide. However, buffering the packet during congestion or during microburst or any other resource, you basically delaying that packet for a longer period of time, which means you're adding jitter. If we talk about how the jitter looks like on the wire, basically this is a steady stream of packets. Each of them have equal space between the packets. They're all coming in the same order. There is no delay. However, as soon as you buffer the packets, you don't know how they're going to be scheduled because you have multiple queues and some of them can be delayed. That way you get a first packet, but then there is some delay. Second packet, there is a bit little delay. Then third packet, and there is more delay, and so on and so on, which means your multicast stream and your video might be a bit flaky, let's put it that way. From that perspective, making a network to forward those traffic in the fastest possible way, it's the goal, and avoiding jitter in this case. Okay, there is always a question, how much of the buffer it's enough buffer? There is no math there. It basically depends what you want to achieve and how you want to do it. However, some advices which I can share is that your real-time traffic should forward traffic immediately in a soon possible way with the lowest latency, with the lowest jitter. And from that perspective, switch must have enough buffer to sustain those kind of burst or that kind of traffic patterns, but also deliver it in time and not delay it too much. Also, dynamically shared buffer architecture allows flexible use of that buffer, because in case that your unicast stream it's congested, you can take a larger portion of the buffer. In case that your multicast stream is delayed, you can take a larger portion of buffer. As I mentioned, it's dynamically allocated to ports and streams which are requiring that buffer. That way, depends on the architecture or depends who is needing that buffer can get the portion of that buffer. Also, in case that you want to protect certain types of traffic, you can also introduce a reservation of that buffer resources in both of the architectures and say, hey, I want to preserve my buffer for this particular stream or this particular port, and that's where I'm going to keep it, but all other will be able to share other portion of the buffer which is present on the switch. Okay, there is something which is called quality of service. Did anybody heard about that? Okay, perfect. Quality of service can be implemented, and that basically covers majority of the stuff which I have talked, which means you will divide your different class of traffic in different queues, different classes, and you will treat it differently. As I mentioned before, your live traffic, it's very, very sensitive on the jitter, or delayed, sorry, and from that perspective should be treated and put in the queue which has highest priority value. However, your live traffic can be delayed. It's not that bounded to come in the shortest period of time, and you can give it to some other queue. If you have additional resources for the traffic or additional traffic in your network, it can take different set of queues, but if that's completely, let's say, irrelevant traffic from perspective of jobs or delay, you definitely can pick it a lower, even lower sensitive queue, lower priority queue, and deliver that traffic in a different way or delayed. In this case, with QoS implemented, your live traffic as well as your file-based or file transfer traffic can coexist in the same network, as each of them has its own properties and will be treated in a different way, they definitely can coexist in the network. Let's conclude. As I mentioned and explained in that diagram which I previously had, head-of-line blocking should be avoided by any case. And from that perspective, your multicast traffic doesn't use ingress buffer. It uses only that egress buffer if you have a VOQ architecture. Your 2110, but not specifically 2110, but also 2022-6 traffic, because it's sensitive to the latency and delay, should be placed in the strict priority queue, and from that perspective forwarded in most efficient way towards the destination. Other traffic, as I said, can be placed in a lower priority queue, lower than strict priority queue, to be delivered in reasonable fashion towards the destination, but still not saturate and not affect the live traffic present in the network. And also, you can implement QoS to achieve this multiple levels of networking and traffic scheduling to protect your live traffic from all other traffic, but also satisfy all the requirements for all other traffic. With this, I would like to thank you for sitting here, and if you have any questions, please let me know.
Well, great. Thank you very much.
Thank you, Wes.
First of all, does anybody in the audience have any questions?
Yep.
Go ahead.
What parameters of the traffic do you look at to determine the priority? Is it just layer 2 or layer 3 and higher?
Basically, the question was, I guess you heard it, what are the parameters to determine what traffic goes into each queue? When we talk about QoS, usually there are markings which are present in the packet itself. And if we talk about layer 2, there is class of service field which sits in the VLAN packet. Maybe I go too deep with this, but basically there is priority value which is present in the packet. When we talk about layer 3, which is in most cases traffic which we have in the network, in the media networks, there is something which is called type of service field, which is present in the IP packet, which can have markings like DSCP or IP precedence. Depends how many beats you want to use in the particular packet. Those are parameters which you can use. However, you also can use and classify traffic based on the type. Let's say that you know that multicast traffic has a different destination address, which sets only a last subnet starting 224 and after. You can classify it based on that. You can classify it based on the source if you know that your group of gateways in one subnet versus your live traffic, it's in a different subnet. Basically, you have wide variety of 5 tuple, how we call it, which is source MAC, destination MAC, source IP, destination IP, and the field, a port, L4 port, to classify it based on that, in addition to priorities which are present there, like COS or DSCP. Make sense? Correct. That would be a manual configuration on the switch, because each of the customer has its own requirements and has its own network, and they best can determine what traffic can be treated in what way.
Yeah, as I always like to point out, if you're working for a bank, video might be your low priority traffic.
Exactly.
Whereas a broadcaster video is a high priority.
Yes.
Any other questions? I just had one real quick one. When we were formulating ST 2110-21, we put in this beta factor, this 1.1, to sort of accommodate buffering and things like that. Is that, and that was, how should I say it, not necessarily based on extensive experimental testing. Do you see that value being approximately right for the state of networking equipment today, or is it way too high, way too low? What's your feeling on that?
I'm not familiar with the value itself. Does it speed up the transfer?
Basically, the 1.1 says that you're going to drain your network buffer 10% faster than you're going to fill it. That's kind of the kind of the model. So basically, if you back into it, you end up with, if you have a 3 gigabit stream, you got to sort of allocate 3.3 gigabits. Yeah.
Yeah.
Is that are we in the right ballpark, or is that?
You are probably in the right ballpark, as I mentioned in this whole presentation, you want to keep your sensitive 2110 traffic least amount possible in the network and deliver it. And in that, if you can drain it faster, you basically don't use any buffer, which means you don't introduce any additional latency or jitter than what it's specifically need for the network. From that perspective, I think that was a really good move.
All right. Well, good. Hey, we get it right sometimes. Okay. Well, that's it, I think. So thank you very much.
Thank you.
By the way, I want to point out to everyone that all of these presentations are being recorded on video, and we will have those videos posted at vsf.tv. So it's real easy, VSF up there, just .tv. So you'll have the ability to go in, look at the videos. We'll also provide PDF copies of a lot of the presentations as well. Actually, it should be all of them. So we'll be looking for those, and they should be posted fairly soon. The videos are actually should be there within a week or so, with all the metadata and everything like that. So hopefully that will be achievable, and we're looking forward to having lots of traffic on the website and seeing how things go. Also, don't forget to scan your badge at the door on the way out if you didn't on the way in. That will send you a link to how to get all the presentations and everything like that. But videos, just go to vsf.tv or the VSF YouTube website. Okay? So we'll be starting up in another couple of minutes with our final speaker for the day. Thank you.